Good morning. This is the last class on our module nuclear reactions. Now, in this session, we will learn about resonance reaction. Now, in the last class, we have already discussed about compound nucleus reactions. Now, we have treated those reactions that is the compound nucleus reactions treats the unbound nuclear states as if they are formed in a structureless continuum. That is, this compound nucleus reactions, or in that model we have considered nuclear states or unbound nuclear state as a structureless continuum. That means there will be a number of nuclear states, and those nuclear states are packed very closely together so that they will appear like a continuous spectrum. Now, each of these nuclear states are considered as discrete states. Hence, they will be unstable and very soon they will decay, and so definitely they will possess a certain width. So, if that nuclear states are having a width, that means they are unstable and they will decay quickly, and at the same time they are discrete. So, when the states are so numerous, that is, when there are a number of such states, then their spacing will be very small when compared to the width of the individual state. So, the final result or the final outcome will be a continuum. So, the compound nucleus will have a continuum structure. That is about compound nuclear states. Now, at the other end of the compound nuclear state, or at the extreme end of the compound nuclear state, we have the bound state. It is studied by direct reactions. And why? Because now, compared to this compound nuclear state, the bound states are stable against particle emission. That means their mean life will be longer when compared to compound nuclear state, and as a result, since they are stable, their width will be small. So, compound nuclear state and bound state are the two extremes of the same scale. Compound nuclear state is an unstable state. They will decay and it is having a discrete structure and their width will be high, whereas a bound state is stable, so they will not decay and their width is small. Now, in between these two states, that is between this compound nuclear state and the bound state, you have a resonant state or resonance region, and it is also called as, or it can also be defined as, the discrete level in the compound nucleus region. Now, these resonance states or the resonance level have a high probability of formation and their width will be small because at low incident energy, the quasi-bound state that is formed will only have two modes of decay. One is re-ejecting the incident particle in the form of elastic or inelastic scattering, and the other is gamma emission. Now, in order to understand about the formation of resonance, here they are presenting a nuclear potential which is seen by a captured particle. So, from this figure, it shows that depending on the phase of the wave function inside the nucleus, we can see a very smooth matching in the variations between relative amplitude of the wave function inside and outside the nucleus. In first case, in case A, incident particle has a little probability of penetrating through the nucleus and form a quasi-bound state. In case C, there is a high probability of penetration. Now, as we vary the energy of the incident particle, we vary the relative phase of the inner and outer wave functions. But the matching point and the relative amplitude will vary accordingly. Now, only for certain incident energy we achieve the conditions as shown in part C, and those energies are called energy of cross section in energy of resonance in cross section. So this is a brief description. The same thing is repeated in that column. Now some mathematical interpretation. In a single isolated resonance of energy ER and width uh, tau, the energy profile of cross section will have the character of energy distribution of any decaying state of lifetime. That is, it is enough that you write in a single, let the isolated resonance energy be ER and let it have a width tau, then decaying state of lifetime of that isolated resonance states is given by this equation. Okay. Resonance occurs when total cross section has a maximum. Then this sentence also you have to write. Then the shape of resonance is obtained by expanding the phase shift about the value pi by 2. Now the width tau is defined as this one. It is enough to write this. No need of mentioning this. Now, since tau is the full width of the resonance, cross section fall to half of the central value, that is this one, E minus ER is equal to this one. Okay, so that is enough. No need of mentioning the cos delta values. Then the scattering cross section you can mention by equation 1. No need of writing this equation. Then the result of the scattering cross section given by equation 1 can be generalized in two ways. In the first case, we take into account the effect of reacting particles with the spin. Okay, if SA and XS are the spins of the incident and target particle, and if I is the total angular momentum of the resonance, I is given by SA plus SX plus L, then the factor 2L plus 1 is replaced by a more general statistical factor G, and G reduces to 2L plus 1 for spinless particle. This is in the case of spin particles. The value of G is this expression for the particles with the spin, whereas the expression for G will be 2L plus 1 for spinless particles. So in this slides, you can mention this what is written in that column, and then write in a single isolator, let ER be the isolated resonance energy of width tau. Then the decaying state of lifetime is given by tau is equal to h cut by this one. Then the resonance occurs when total cross section is maximum. Then you have to write this sentence. Then the width tau is defined by this expression. No need of this. Then because tau is the full width of the resonance, this sentence you have to mention. No need of writing this occurs when that cos delta value, this up to this you can skip. No need of writing. Then write about the scattering cross section given by equation 1 and this full paragraph. Okay, now that is the first generalization. Now the second change that we take into account is we allow partial entrance and exit widths. That is, if the resonance has many ways to decay, then total width tau is the sum of all partial width tau I, that is tau equal to sigma I tau A. The tau square factor in denominator of equation 1 is related to decay width of resonant state and therefore to its lifetime T equal to h by h cut by tau. The observation of only a single entrance or exit channel does not affect this factor, for the resonance always decays with the same lifetime. Then okay, all this sentence you can mention. Then the tau square factor in the numerator of equation 1, they are discussing about the significance of tau square that appears in the numerator and denominator of equation 1. This is about tau square that appears in the denominator of equation 1. This is about the significance of tau square that appears in the numerator of equation 1. It is related to the formation of resonance and to its probability to decay into a particular exit channel. In the case of elastic scattering, entrance and exit channels are identical. That is, for the reaction A plus X giving A plus X, we should use the partial width TAX of the resonance and exit channels. So you can mention equation 2. Similarly, for another equation, a different exit width will be used, equation 3. So this slide you can write. This full slide you have to mention. Equation 2 and 3 are examples of Britt-Wiener formula for the shape of a single isolated resonance. So, since this equation 2 and 3 represents this formula, definitely you will have to mention the full slide, this slide. Okay. Most of the elastic scattering resonance will have shape different from that suggested by this formula. Why? Because this originates with another contribution to reaction amplitude from direct scattering of incident particle by nuclear potential without forming resonant state. This different alternative process is called potential scattering or shape elastic scattering. So that also you can write, because there is a probability of asking a question like mention or what is meant by potential scattering or shape elastic scattering. Okay. Now both these scattering, that is potential scattering and resonance scattering, contribute to elastic scattering amplitude, and the interference between these two processes will cause variation in the cross section. Interference can cause the combined cross section to be smaller than it would be for either process alone. Okay, so it is enough that you mention up to this. That is up to this much is enough from this slide. Okay. Now this is the expression that we have already wrote for the cross section that you can write. Then for regions far from the resonance, this particular term will be very much large compared to gamma by 2, and the potential scattering term will be given by this expression. Now at E equal to ER, resonant term will dominate, and it is given by this equation. Now near the region of resonance, there will be an interference between these two terms, and that will produce the characteristic shape as shown in the figure. Just draw a rough sketch. Okay. Now instead of mentioning this one, so up to this much you will have to write when you are asked the essay question. Just skip those paragraphs that I told not to write. Okay. Okay, thank you.